Statistical inference is the process of deducing properties of an underlying distribution by analysis of data. Inferential statistical analysis infers properties about a population. This includes testing hypotheses and deriving estimates. The population is assumed to be larger than the observed dataset. In other words, the observed data is assumed to be sampled from a larger population. Inferential statistics can be contrasted with descriptive statistics. Descriptive statistics is solely concerned with properties of the observed data, and does not assume that the data came from a larger population. Introduction. Statistical inference makes propositions about a population, using data drawn from the population with some form of sampling. Given a hypothesis about a population, for which we wish to draw inferences, statistical inference consists of selecting a statistical model of the process that generates the data and deducing propositions from the model. Konishi and Kitagawa state, the majority of the problems in statistical inference can be considered to be problems related to statistical modeling. Relatedly, Sir David Cox has said, how the translation from subject matter problem to statistical model is done is often the most critical part of an analysis. The conclusion of a statistical inference is a statistical proposition. Some common forms of statistical proposition are the following. A point estimate, i.e., a particular value that best approximates some parameter of interest. An interval estimate, e.g., a confidence interval, i.e., an interval constructed using a dataset drawn from a population so that, under repeated sampling of such datasets, such intervals would contain the true parameter value with the probability at the stated confidence level. A credible interval, i.e., a set of values containing, for example, 95% of posterior belief. Rejection of a hypothesis. Clustering or classification of data points into groups, models and assumptions. Any statistical inference requires some assumptions. A statistical model is a set of assumptions concerning the generation of the observed data and similar data. Descriptions of statistical models usually emphasize the role of population quantities of interest, about which we wish to draw inference. Descriptive statistics are typically used as a preliminary step before more formal inferences are drawn. Degree of models, assumptions. Statisticians distinguish between three levels of modeling assumptions: fully parametric. The probability distributions describing the data generation process are assumed to be fully described by a family of probability distributions, involving only a finite number of unknown parameters. For example, one may assume that the distribution of population values is truly normal, with unknown mean and variance, and that datasets are generated by simple, random sampling. The family of generalized linear models is a widely used and flexible class of parametric models. Non-parametric. The assumptions made about the process generating the data are much less than in parametric statistics and may be minimal. For example, every continuous probability distribution has a median, which may be estimated using the sample median or the Hodges-Lehmann-Sen estimator, which has good properties when the data arise from simple random sampling. Semi-parametric. This term typically implies assumptions in between fully and non-parametric approaches. For example, one may assume that a population distribution has a finite mean. Furthermore, one may assume that the mean response level in the population depends in a truly linear manner on some covariate but not make any parametric assumption describing the variance around that mean. More generally, semi-parametric models can often be separated into structural and random variation components. One component is treated parametrically and the other non-parametrically. The well-known Cox model is a set of semi-parametric assumptions. Importance of valid models, assumptions. Whatever level of assumption is made, correctly calibrated inference in general requires these assumptions to be correct, i.e., that the data-generating mechanisms really have been correctly specified. Incorrect assumptions of simple, random sampling can invalidate statistical inference. More complex semi- and fully parametric assumptions are also cause for concern. For example, incorrectly assuming the Cox model can in some cases lead to faulty conclusions. Incorrect assumptions of normality in the population also invalidate some forms of regression-based inference. The use of any parametric model is viewed skeptically by most experts in sampling human populations. Most sampling statisticians, when they deal with confidence intervals at all, limit themselves to statements about estimators based on very large samples, where the central limit theorem ensures that these estimators will have distributions that are nearly normal. In particular, a normal distribution would be a totally unrealistic and catastrophically unwise assumption to make if we were dealing with any kind of economic population. Here, the central limit theorem states that the distribution of the sample mean for very large samples is approximately normally distributed. If the distribution is not heavy-tailed, approximate distributions, given the difficulty in specifying exact distributions of sample statistics. Many methods have been developed for approximating these. With finite samples, approximation results measure how close a limiting distribution approaches the statistics sample distribution. For example, with 10,000 independent samples, the normal distribution approximates the distribution of the sample mean for many population distributions by the Bayesian theorem. Yet for many practical purposes, the normal approximation provides a good approximation to the sample means distribution when there are 10 independent samples. According to simulation studies and statisticians' experience, following Kolmogorov's work in the 1950s, advanced statistics uses approximation theory and functional analysis to quantify the error of approximation. In this approach, the metric geometry of probability distributions is studied. This approach quantifies approximation error with, for example, the Kullback-Leibler divergence, Bregman divergence, and the Hellinger distance. With indefinitely large samples, limiting results like the central limit theorem describe the sample statistics limiting distribution. If one exists, limiting results are not statements about finite samples, and indeed are irrelevant to finite samples. However, the asymptotic theory of limiting distributions is often invoked for work with finite samples. For example, limiting results are often invoked to justify the generalized method of moments and the use of generalized estimating equations, which are popular in econometrics and biostatistics. The magnitude of the difference between the limiting distribution and the true distribution can be assessed using simulation. The heuristic application of limiting results to finite samples is common practice in many applications, especially with low-dimensional models with log-concave likelihoods. Randomization-based models for a given dataset that was produced by a randomization design. The randomization distribution of a statistic is defined by evaluating the test statistic for all of the plans that could have been generated by the randomization design. In frequentist inference, randomization allows inferences to be based on the randomization distribution rather than a subjective model, and this is important especially in survey sampling and design of experiments. Statistical inference from randomized studies is also more straightforward than many other situations. In Bayesian inference, randomization is also of importance. In survey sampling, use of sampling without replacement ensures the exchangeability of the sample with the population. In randomized experiments, randomization warrants a missing at random assumption for covariate information. Objective randomization allows properly inductive procedures. Many statisticians prefer randomization-based analysis of data that was generated by well-defined randomization procedures. Similarly, results from randomized experiments are recommended by leading statistical authorities as allowing inferences with greater reliability than do observational studies of the same phenomena. However, a good observational study may be better than a bad randomized experiment. The statistical analysis of a randomized experiment may be based on the randomization scheme stated in the experimental protocol and does not need a subjective model. However, at any time, some hypotheses cannot be tested using objective statistical models, which accurately describe randomized experiments or random samples. In some cases, such randomized studies are uneconomical or unethical. Model-based analysis of randomized experiments. It is standard practice to refer to a statistical model, often a linear model, when analyzing data from randomized experiments. However, the randomization scheme guides the choice of a statistical model. It is not possible to choose an appropriate model without knowing the randomization scheme. Seriously misleading results can be obtained analyzing data from randomized experiments while ignoring the experimental protocol. Common mistakes include forgetting the blocking used in an experiment and confusing repeated measurements on the same experimental unit with independent replicates of the treatment applied to different experimental units. Paradigms for inference. Different schools of statistical inference have become established. These schools, or paradigms, are not mutually exclusive, and methods that work well under one paradigm often have attractive interpretations under other paradigms. Bandyopadhyay and Forster described four paradigms: classical statistics or error statistics, Bayesian statistics, likelihood-based statistics, and the Akaikine information criterion-based statistics. The classical paradigm, the Bayesian paradigm, and the AIC-based paradigm are summarized below. The likelihood-based paradigm is essentially a sub-paradigm of the AIC-based paradigm. Frequentist inference. This paradigm calibrates the plausibility of propositions by considering repeated sampling of a population distribution to produce datasets similar to the one at hand. By considering the dataset's characteristics under repeated sampling, the frequentist properties of a statistical proposition can be quantified, although in practice this quantification may be challenging. Examples of frequentist inference: p-value, confidence interval, frequentist inference, objectivity, and decision theory. One interpretation of frequentist inference is that it is applicable only in terms of frequency probability, that is, in terms of repeated sampling from a population. However, the approach of Neyman develops these procedures in terms of pre-experiment probabilities, that is, before undertaking an experiment. One decides on a rule for coming to a conclusion such that the probability of being correct is controlled in a suitable way. Such a probability need not have a frequentist or repeated sampling interpretation. In contrast, Bayesian inference works in terms of conditional probabilities, compared to the marginal probabilities used in the frequentist approach. The frequentist procedures of significance testing and confidence intervals can be constructed without regard to utility functions. However, some elements of frequentist statistics, such as statistical decision theory, do incorporate utility functions. In particular, frequentist developments of optimal inference make use of loss functions, which play the role of utility functions. Loss functions need not be explicitly stated for statistical theorists to prove that a statistical procedure has an optimality property. However, loss functions are often useful for stating optimality properties. For example, median unbiased estimators are optimal under absolute value loss functions, in that they minimize expected loss. And least squares estimators are optimal under squared error loss functions, in that they minimize expected loss. While statisticians using frequentist inference must choose for themselves the parameters of interest, and the estimators test statistic to be used, The absence of obviously explicit utilities and prior distributions has helped frequentist procedures to become widely viewed as objective. Bayesian inference. The Bayesian calculus describes degrees of belief using the language of probability. Beliefs are positive, integrate to 1, and obey probability axioms. Bayesian inference uses the available posterior beliefs as the basis for making statistical propositions. There are several different justifications for using the Bayesian approach. Examples of Bayesian inference: credible interval for interval estimation, Bayes factors for model comparison. Bayesian inference, subjectivity and decision theory. Many informal Bayesian inferences are based on intuitively reasonable summaries of the posterior. For example, the posterior mean, median and mode, highest posterior density intervals, and Bayes factors can all be motivated in this way, while their user's utility function need not be stated for this sort of inference. These summaries do all depend on stated prior beliefs, and are generally viewed as subjective conclusions. Formally, Bayesian inference is calibrated with reference to an explicitly stated utility, or loss function. The Bayes rule is the one which maximizes expected utility, averaged over the posterior uncertainty. Formal Bayesian inference therefore automatically provides optimal decisions in a decision-theoretic sense. Given assumptions, data and utility, Bayesian inference can be made for essentially any problem. Although not every statistical inference need have a Bayesian interpretation, analyses which are not formally Bayesian can be incoherent. A feature of Bayesian procedures which use proper priors is that they are guaranteed to be coherent. Some advocates of Bayesian inference assert that inference must take place in this decision-theoretic framework, and that Bayesian inference should not conclude with the evaluation and summarization of posterior beliefs. AIC-based inference. Other paradigms for inference: minimum description length. The minimum description length principle has been developed from ideas in information theory and the theory of Kolmogorov complexity. The principle selects statistical models that maximally compress the data. Inference proceeds without assuming counterfactual or non-falsifiable data-generating mechanisms, or probability models for the data, as might be done in frequentist or Bayesian approaches. However, if a data-generating mechanism does exist in reality, then according to Shannon's source coding theorem it provides the MDL description of the data, on average and asymptotically. In minimizing description length, MDL estimation is similar to maximum likelihood estimation and maximum a posteriori estimation. However, MDL avoids assuming that the underlying probability model is known. The MDL principle can also be applied without assumptions that, e.g., the data arose from independent sampling. The MDL principle has been applied in communication coding theory and information theory, in linear regression, and in data mining. The evaluation of MDL-based inferential procedures often uses techniques or criteria from computational complexity theory. Fiducial inference. Fiducial inference was an approach to statistical inference based on fiducial probability, also known as a fiducial distribution. In subsequent work, this approach has been called ill-defined, extremely limited in applicability, and even fallacious. However, this argument is the same as that which shows that a so-called confidence distribution is not a valid probability distribution, and since this has not invalidated the application of confidence intervals, it does not necessarily invalidate conclusions drawn from fiducial arguments. Structural inference. Developing ideas of Fisher and Pittman from 1938 to 1939, George A. Barnard developed structural inference, or pivotal inference, an approach using invariant probabilities on group families. Barnard reformulated the arguments behind fiducial inference on a restricted class of models on which fiducial procedures would be well-defined and useful. Inference topics. The topics below are usually included in the area of statistical inference. Statistical assumptions. statistical decision theory, estimation theory, statistical hypothesis testing, revising opinions in statistics, design of experiments, the analysis of variance and regression, survey sampling, summarizing statistical data.